and welcome Mindsets to this session of Learn Extra. Today, guys, we're going to be doing some science with grade 11s, so I hope you guys are ready. You've got your pens and pads out. I'm Ty, and I'm here with Bruce, who's going to take us through today's lesson. Bruce, what are we doing today?
Great, Ty. We've got a great lesson today, guys. We're having a look at a section called Momentum and Impulse.
Okay.
It's one of the mechanics sections, and we're going to be talking about motion related to mass, velocity, all that sort of stuff, and the forces that are involved in there. So we've got quite a full lesson today, Ty.
All right, awesome.
Great.
Okay, so while you make your way across
Thank you.
the board,
Great.
no problem. Mindset is, you know the drill by now. You need to get on the page. You know the link, www.facebook.com/learn extra. Talk to me. Let me know what you guys are thinking. Let me know if you guys are lost in you. If you need help, post on the page and let me know, because I can't help you if you don't help yourself by posting on the page. And yes, I have this awesome Casio calculator and this labeler to give away. So Mindsetters, please make my job easy and post on the page. But for now, we have a lesson to get to. Thank you to Liberty for sponsoring the show. And on that note, Bruce, take it away.
Great. Thanks very much, Ty. And hi there, guys, once again, and welcome to tonight's show. As I said in the introduction, we're going to be having a look at one of our mechanics sections entitled Momentum and Impulse. Now, a lot of schools, I know in grade 11, do this particular section a little bit earlier on in the year. And if you have done it, that's brilliant, because then we can use this as revision. So hopefully for your end of year exams, this will then come as sort of a little bit of a boost to practice some problems, make sure we understand the theory. The guys who are busy doing it, or maybe you still got to do it, well, just have to follow closely and watch it. Make sure that we try and understand as much as we can. It will help you as you start developing and building up your idea and understanding of momentum. But guys, let's start off with a very broad and general overview of what we mean by the concept of momentum. The main thing, guys, is that any moving object has got momentum. Okay, and you might have heard this word being used quite, I won't say casually, but being used often around in general conversation. That person really is moving with a lot of momentum, or that car is going past with a lot of momentum. Okay, guys, that object is moving. Okay, if an object moves, it's got momentum. So how do we then physically put down the quantities to allow us to calculate how much momentum that object has? Well, guys, there are two main factors that we have to have a look at. One of them is mass. What is the mass of the object? And secondly, what is the velocity at which that object is traveling? Those are the two things that allow us to calculate and determine an object's momentum. The mass of the object and the speed or velocity at which it's traveling. So let's have a look at the board, and I've put down a couple of little ideas here for you. And I've spoken about momentum as a physical quantity which is related closely to forces. And whoops, let's get the pen working. Related closely to forces, all right? And I want to talk a little bit more about how it's related to forces a little bit later, okay? But the main thing is, there it is, momentum is a property which applies to moving objects, all right? So an object has to be moving to have momentum. So therefore, if you ask to define momentum, what are the important things that we must include in our definition? Okay, well, let's have a look. Momentum is the tendency of an object to continue to move in the direction of travel. Right, so in other words, that object must be able to move. It must be in motion. It can't be stationary. It has to be in motion, and it must be moving in a particular direction. Okay. Then the second bit, which I'm actually going to bracket, now becomes our core understanding of that concept of momentum. Momentum is calculated from the product of the mass and the velocity of an object. And here, guys, and I'm just going to put a nice circle around that word there, it's the product. Okay, so guys, straight away, if we're dealing with the mass of the object and the velocity of the object, we are going to multiply those two quantities together. That will give us the total momentum of that object. So let's have a look at the little calculation. So there's the object over here, all right, and that object is moving. It's got a mass, it's got a velocity. There's the direction of motion. Momentum is the mass multiplied by the velocity. And here, guys, is our formula for calculating momentum. Now, interesting, you probably say, well, you've got a symbol there. P is equal to m times v. Where does this symbol P come from? Well, guys, the symbol for momentum is lowercase p. And I want to just make sure, whoops, the pen is just getting a little carried away here. Let's go back and try that one again. That lowercase p is the symbol for momentum. All right. So please, guys, don't think now, well, m for momentum. All right? Can't be, because m is for mass. All right, so we use the symbol lowercase p. So p is equal to m times v. And therefore, what units? What do we measure momentum in? Well, it's quite easy, because if we measure mass in kilograms, okay, and velocity in meters per second, guess what we've got as our unit of momentum? It's the kilogram meter per second. Kilogram meter per second. Now, guys, that is the unit. We don't have a shortened or an abbreviated unit for it. So we have to make sure that we are talking about the kilogram meter per second. All right. Now, another thing that I want to talk specifically about when it comes to momentum is that if it's the mass times the velocity, this velocity over here has to be a constant velocity. All right. It has to be a constant velocity. So in other words, we are dealing with, at this stage, a constant velocity situation. All right. If the velocity of the object changes, then the momentum is also going to have to change. All right. And we're going to have a look at this thing called change in momentum a little bit later. But it's very important to establish the fact right now. So if you're wanting to work out the momentum of an object traveling at a certain speed or velocity, we have to talk about that speed or velocity remaining constant. If we change the velocity, we will then change the momentum of the object. Now, the other quick question is, before we move on, if we change the velocity, what's causing that velocity to become changed? And that, guys, is what I've put in over here. We are going to have a force. Okay. And that's when we said right in the beginning that momentum can be related to the force. And the force will change the velocity. Now, the question is, what type of force will cause the velocity to change? Now, think about it. If velocity changes, and I'm just going to get a little open thing over here. So, if we've got a force, okay, and we want the force which we're going to allow to change the velocity. Okay. If you remember all the way back to your physics, especially your mechanics, okay, and we're going to change the velocity. A force that changes the velocity is going to produce an acceleration. A change in velocity always means that the object is accelerating. If my velocity gets bigger, then we've got a positive acceleration. If my velocity slows down, I've got a negative acceleration. And from Newton's second law, what do we call that force that changes the velocity? Well, it's going to be called the net force. Okay, and the net force produces acceleration, and acceleration produces a change in velocity. Okay. Remember, acceleration, the symbol is A, and the change in velocity we often call delta V. So guys, there's some very important little concepts that we're going to have to bring in, and we're going to have to use when we start talking about our momentum. Okay, and the important thing is, guys, is that momentum will get related to forces, because if we change the momentum, we have to introduce a net force. Okay, but before we get on to that more complicated sort of stuff, what I thought we'd do is just do some couple of nice, easy, sort of simple type of problems, have a look and see how they work, make sure that we can write them down, the layout is correct, and then we can introduce our topics as we go along. Okay, so I'm going to go back to my original slide over here, and I'm going to get down, we've just spoken about there, And I've put a little question up on the board. And it's a nice, simple little problem. And hopefully a lot of you guys will be able to do it pretty easily as I go through it with you on the board. And I've got here a soccer ball of mass 420 grams is kicked at 20 meters per second towards the goalpost. Calculate the momentum of the ball. Now, guys, we've got to assume that if that ball is being kicked with a velocity of 20 meters per second, that velocity is going to remain the same to work out the momentum of the ball. Okay. Or we have to say, well, that's the velocity at that particular time, therefore that's the momentum at that particular moment in time. So how do we work it out? Well, there's our formula. Momentum is mass times velocity. Very important to change our 420 grams into kilograms. Now, guys, how do we do that? How do we work out or convert grams into kilograms? Well, that basically is all it's, whoops, I'll rub that out. That's going to be basically done in terms of our factor. And all we have to say is, how many grams are there in a kilogram? And a lot of you guys will be able to tell me that 1,000 grams equals 1 kilogram. So if 1,000 grams is equal to 1 kilogram, therefore what do? All it is 420 divided by 1,000, and that is how we are able to convert our mass into kilograms. Okay, guys, we have to. We cannot leave the mass in grams. It's one of the non-negotiables that we have to do in this section. The velocity of 20 meters per second, and all we have to do is simply multiply. So momentum is going to be 0.42 multiplied by 20, and we get ourselves an answer of 8,4 kilogram meter per second. In other words, the momentum of that soccer ball, of that mass traveling at that speed, is 8,4 kilogram meter per second. So guys, pretty straightforward, pretty easy, pretty nice small little formula to worry about. We don't have to get too stressed about it. But what I said earlier is what happens if we change the momentum. Okay, and this is where the important stuff starts to come in. Because if we change the momentum, there has to be a change in velocity. So let's have a look now at how we can calculate change in momentum. And what I've got over here is a little situation. And I've put here, let's consider a tennis ball. It's got a mass of 0.1 kilograms that is hit with an initial velocity of 5 meters per second and bounces back off a wall at a final velocity of 3 meters per second. So can you see, guys, that the velocity has changed? We have got a change in velocity. And if we have a change in velocity, we must have a change in momentum. So let's have a look at my diagram, okay? And there's the ball, okay? So there's the ball, 0.1 kilogram. And it's moving, I've put it from left to right, moving with a velocity of 5 meters per second. Okay. Now, what I've put here is that when it now hits the wall at this point, what's going to happen is that ball is going to bounce backwards. We all know that a tennis ball, we often stand there and throw that tennis ball against the wall, and we can catch it. The tennis ball is able to hit the wall and bounce back. Okay. It'll have a momentum as I throw it, and there'll be momentum due to the velocity when it bounces back. So we have to now introduce that into our situation. So when it moves away from the wall, it has a different momentum called the momentum after the collision with the wall. So in other words, here in this diagram, can you see now I've bounced back? It's going to have momentum after collision with the wall. So beforehand, before it hit the wall, momentum before collision with the wall, and then it's bounced back momentum after collision with the wall. So how do we tie this all up to do this calculation? Well, very simple. All we have to do is say, thus we have a change in momentum of the tennis ball, and the change in momentum, there it is momentum after minus, whoopsie, I just need to cross that out. It should be momentum before. There's a little typing error there. I'll just change it. So in other words, we always look momentum after minus momentum before, or what a lot of people like to say, the final momentum minus the initial momentum. And that's what I've put over here. Momentum after minus momentum before. and therefore it's going to be mv after minus the momentum before, and I'm going to just have a quick help you with, let's get this over here, and let's bring this up to make it a little clearer. So if my momentum before equals mv, and my momentum after also equals mv, okay? That's going to be momentum before, my momentum after, and what a lot of people like to say, a momentum initial, and my momentum final, okay? My change in momentum, which is delta P, is always going to equal momentum after minus momentum before, okay? Which means it's going to be mv final minus mv initial, okay? mv final minus mv initial. And if we have a look at that little equation, can you see now that we have a common factor that we can remove to simplify the equation? And that common factor is going to be the mass. So let's remove the mass. So delta P is equal to m, okay? And all we have to say is V final minus V initial. And there, guys, we have, and I've developed it a little bit more easily for you, we've developed an equation to allow us to calculate the change in momentum. Crucial, we must know what the initial and final velocities are to allow us to work out the change in momentum. So if we go back to my original slide over here, you will see now, let's bring it back and scroll down a little bit. Where are we going? There we go. There it is. Delta P is equal to mvf minus vi. Or, and then we can tidy this up, delta P, my change in momentum, is equal to m delta V. And the delta V there is simply the change in velocity, the final velocity minus the initial velocity. So guys, it's very simple to work out the change in momentum of an object. Okay, so let's have a look now at a little calculation. Well, let's use our values over here. Well, we've got a 5 meter per second, 5 meters per second velocity of the ball coming in, and we have got a 3 meter per second, so let's put that in over here, 3 meter per second of the ball bouncing out. So if we've got delta P is equal to m delta V, okay, we know that the mass is constant at 0.1. My final velocity is going to be 3 meters per second, and my initial velocity is going to be 5 meters per second. Now, there's one important thing that we're going to have to make sure we understand before we can continue with this problem, and that is momentum is a vector quantity. In other words, momentum has got both magnitude and direction. And a lot of you guys will be jumping up and saying, aha, because if we've got the tennis ball, if we've got the tennis ball, which has been thrown against the wall in that direction and then bounces off in that direction, we've got two different directions, haven't we? And if we've got two different directions, then we must have one direction being positive and the other direction being negative. So we have to take the vector component or the vector aspect of momentum into consideration, which means then if it's moving to the right in a positive direction, it's going to be moving to the left in the negative direction. Therefore, the final velocity, which is now moving away from the wall to the left, is going to equal minus 3 meters per second, which means then, guys, that we have to put a negative value for our VF in the calculation. And therefore, when we substitute, sorry, I'm going to just move it over here to make it a little bit more easy for you. Okay, we've got delta P is equal to m delta V, and therefore 0.1 is equal to, well, VF is now minus 3. VI is going to be 5. So minus 3 minus 5, because it's going to be the change in velocity, final minus initial, which means it's going to equal 0.1 times minus 8. And that's going to give me minus 0.8 kilogram meter per second as my delta P. Notice we get a negative answer. And the crucial thing here, guys, is we've got a negative answer. We have to interpret it. Remember what we had over here? In which direction was negative? It was to the left. So therefore, we are going to have to say delta P is equal to 0.8 kilogram meter per second away from the wall. Away from the wall, which, remember, guys, is to the left, because my sign has been interpreted here. Very important that we do it. I think we take a break. I've got a couple of extra problems which we can do after the break, just to consolidate this all, and then we should have change of momentum sorted out.
Okay, no problem.
Great.
So, on that note, mindsetters, do not disappear, do not go anywhere. Make sure that you stick around and you are back with your pens, pads out, and you have your phones next to you so you can post on the Facebook page. But for now, we're going to see you after this. And welcome back, mindsetters. Hope you had a nice little break there. You went and did whatever you had to do so that you can now sit down, focus, and pay attention. No more distractions. Pay attention. Because right now we've got a lesson that we still need to continue. So do not forget to keep on posting so I can give away this Casio calculator and this awesome labeler. But for now, mindsetters, you know to do the right thing. Pens, pads out, and make notes. But for now, Bruce, take it away.
Right, thank you, Ty. Well, guys, as I said before the break, I want to practice a couple more problems, just working with momentum and changing momentum and looking at a different style of problem, just so we're used to having a look now at these various components, the way we calculate them, and obviously our layout and our setout also very important as well. So what I've got here is a little problem that I'd like to give to you guys, and the first one's not particularly difficult, but it just practices our whole idea of using momentum. And what it says is that a cricket ball of mass 160 grams is bowled at 40 meters per second towards a batsman. Calculate the momentum of the cricket ball. Well, let's have a look. What do we have? Well, we've got the mass of the cricket ball, and we've got the velocity of the cricket ball. We're looking for the momentum. So, guys, a nice, simple problem is momentum is equal to mass times velocity. We've got our mass of 160 grams. Now, guys, remember what we said. We cannot use grams in our calculation. We have to convert to kilograms. How do we do that? We simply divide by 1,000, because there are 1,000 grams in a kilogram, and therefore we get 0.160 kilograms being our answer over there. Okay. Which means then that all I have to do is substitute that in for the mass, multiplied by the velocity. That's nice and easy. That's equal to 40 meters per second. And do we have our calculator is here? So let's bring our calculator up. And what are we doing? We're saying 0.160, and we are multiplying by 40, and we get an answer of, let's get that into a decimal point, 6,4. And there's our answer, 6,4. Whoops, let's bring our pen back after that. 6,4, and that's going to be my momentum, kilogram meter per second. And there's our answer. Okay, notice, guys, we have a positive value, and that means that the momentum is in the direction of the motion. All right, guys, let's not forget our vector component of momentum. Direction is very, very important here. And the second question I'm going to do now is going to help us practice this whole concept of direction once more. And I'm going to go scroll down to this question over here, and there it is. And sorry, let's bring this back up a little bit. A rubber ball of mass 0.8 kilograms is dropped and strikes the floor with an initial velocity, initial velocity of 6 meters per second, and then it bounces back up with a final velocity of 4 meters per second. Calculate the change in momentum of the rubber ball caused by the floor. Well, guys, change in momentum, what do we have? Well, delta P is equal to m delta V. There's my equation for the change in momentum. Okay, scroll down, give a bit more space, and we know that delta P is equal to m, or the change in velocity is the final velocity minus the initial velocity. So guys, there's our second equation there. All right. Now, guys, I've put both of the equations down. I don't mind, whoopsie, this pen sometimes goes a little bit crazy on me. Let's bring it back. There it is. It doesn't matter which equation you use. Both of them are absolutely identical. Okay. So if you're quite happy just to put delta P is equal to m delta V as your equation, or delta P equals m Vf minus Vi, they are identical. Okay. Now, what we've got to have a look at, and I'm going to draw it over here in a little diagram, is that if we've got the floor there, and we've got a ball that's being dropped from an initial height, and that ball now bounces back up, okay? The mass of the ball is remaining constant. The mass of the ball was 0.8 of a kilogram, okay? It now strikes the floor with a velocity of 6 meters per second, okay, and it bounces back up with a velocity of 4 meters per second in the upwards direction. So I'm going to put my arrow like that. Guys, can you see now we've got the concept of direction again? Dropped, so it's downwards and then upwards. So we have to now assign the correct sign for the calculation. We must take the direction change into consideration. Now, guys, the direction that you want to make positive and the direction you want to make negative is up to you. But an easy way to try and remember it is always say, what is my initial direction of motion? In this case, my initial direction of motion was downwards. And if that is downwards, then make your initial direction positive, and which means then that your change in direction, your second direction, is going to be negative. So I'm going to, for this particular calculation, I'm going to take my downwards direction as positive and my upwards direction as negative. Okay, so let's now have a look and let's put this in. So this was my VI, that's my initial, and this over here was my final velocity. Okay, so therefore, let's plug it in. So delta P is going to equal mass of 0.8. Okay, my final velocity over here, there it is. Let's bring it in. My final velocity now is minus 4. Okay, guys, don't forget, and I'm going to make a very, very big box around there. My final velocity is going to be opposite to my initial direction. It's going to be my negative direction. Therefore, my final velocity is going to be minus 4 minus my initial velocity, which is now 6. Okay? And therefore, we're going to have delta P is going to equal 0.8 times minus 10. Now, that's not a very difficult calculation to do, because 0.8 times 10, delta P must now equal minus 8 kilogram meter per second. Okay. Again, guys, look over here. There's my negative sign. It's come up in my answer. We have to interpret the negative sign. The negative sign is going to be in the direction we've assigned it. And remember, guys, we assigned that upwards or away from the floor, bouncing upwards from the floor, will be my direction, which is negative. So therefore, my delta P, my change of momentum, is going to be 8 kilogram meter per second upwards, or we could say away from the floor. Okay. All right. And that, guys, is going to make an examiner very impressed, because he now knows that you're interpreting your signs correctly and you're understanding the vector component of momentum, which is very important. Okay. So, guys, that's how we handle our change in velocity. From there, we need to take our next step. Where are we going now with our next step? Well, remember, right in the beginning, I said if we change our momentum, we have to change our velocity, which we've seen. If we change our velocity, something must be acting in the system to cause that velocity to change. Can you guys remember what I spoke about? Well, if you all turned around and said we have to have a force to change that object's velocity, you're absolutely correct. So to change an object's velocity, okay, we have to have a force. But the question is, what type of force? And the type of force that changes velocity, either increasing it or decreasing it, is always going to be a net or resultant force. Okay, so a net or resultant force will change the velocity, which will change the momentum. So the question is now, how do we incorporate this net or resultant force into our discussions? Because we've now got a change in momentum, how do we now bring it? And this is where I'm going to go to my next slide. Okay, and we are now going to introduce a term which now incorporates this net force. And that is the term called impulse. Okay, and this I know people find a little bit more tricky, a little bit more difficult, because we are now sort of growing this idea, growing the theories, and suddenly maybe the math starts becoming a little bit more tricky. But let's go through it slowly and we'll check it out. Okay. Right, what have I got here? When a resultant or net force acts upon an object for a given amount of time, the object's velocity is changed, and hence the object's momentum is changed. Guys, do you see that? Exactly what I spoke about earlier. So that becomes a very, very pivotal statement when it comes to the understanding of our change of momentum and now this thing called impulse. Okay, it's this guy here, this resultant, or what we call a net force. And how do we now incorporate this? Well, let's remind ourselves a little bit about net forces. That a resultant or net force acting for a given amount of time will change an object's momentum. So what I've got here is that we've got a resultant or net force acting for a given amount of time. So we're introducing another factor. How long is this resultant or net force acting in the system? Okay, and I think it's fairly logical to say that the longer the net force acts, the more the object's velocity is going to change, it's going to be affected. The shorter the time, the less the object's velocity is going to change. And therefore, because of the relationship with momentum, the longer that the net force acts on the system, the greater the change in momentum, the shorter the net force, the less the change in momentum. And I hope that's one of the most important concepts that we need to have a look at. And we'll be practicing this as well as we go through. But let's just have a look and carry on with our thinking. So here's a little reminder of Newton's second law. Okay, so I'm just going to put here Newton's second law. We incorporate now this net force, is that the net force is equal to the mass of the object multiplied by the object's acceleration. Okay. Therefore, how do we now incorporate this? Okay, well, Newton's second law stated that the acceleration of an object is directly proportional, okay, to the resultant or net force acting upon the object, and inversely proportional to the mass of the object. Guys, Newton's second law, most of you guys would have done it, one of the most important and crucial laws when it comes down to mechanics. Okay, we cannot discard or underestimate the importance of making sure that you understand how Newton's second law works in terms of the net or resultant force and the relationship with the acceleration. Okay, so there is the classic definition. Okay, and here we're now going to have a look at some of the stories behind it. If the resultant or net force acts opposite to the object's motion, it slows the object down. Right. So if we are acting opposite to the motion of the object, we will slow the object down. If the resultant or net force acts in the same direction as the object, then the object will speed up. Okay. Very important that we do understand that. The resultant force acts opposite to the direction of motion, we slow it down. if it acts in the same direction as motion, we speed the motion of the object up. In other words, it goes faster and faster. So, how do we put this all together? Okay, and here we go. Either way, the resultant velocity will change the velocity, the resultant force will change the velocity of an object. So therefore, if we take my Newton's second law equation, F net is equal to m times a, and we know from mechanics that acceleration is the change in velocity over the change in time. That we would have done in grade 10, okay? Can you see now that we can substitute this value of a into my Newton's of second law equation? So therefore, we are now ending up with a more modified equation that F net, the resultant force, is equal to mass multiplied by the change in velocity divided by time. And all we have to do now to clean this up is multiply through to put delta t onto the left-hand side of the equation, and we get an equation of F net times delta t equals m delta v. And look at that, guys. Do you see it? M delta v. And a lot of you guys are saying, hang on, I've recognized m delta v. I know exactly where I've seen it before. Well, where have you seen it before? Well, remember that delta p was equal to m delta v. So can you see now, guys, that the net force, the magnitude of the net force, multiplied by how long that net force is acting, is going to equal the change in momentum of that object. Okay, and that is what we know as the impulse. Very important to this last line that I've got down here. The quantity, F net times delta t, is known as the impulse and is equal to the change in momentum of the object. So guys, the word impulse now isn't so scary anymore, is it? The word impulse is simply another way of talking about the change in momentum. However, that change in momentum, or that word impulse, has now got another way of calculating it. Simply by saying that F net delta t is equal to delta p, and that impulse is equal to F net times delta t. And there is a very important link up that we've got. Okay, the impulse is equal to the magnitude of the resultant or net force multiplied by the time it takes. Okay, now guys, there's a lot of theory there, and I've gone through it quite slowly. But what I'm going to do after our little break is that I'm going to do a number of questions that are going to use the idea of impulse, and that we are going to be able to practice and to make sure that we feel comfortable in actually handling this type of equation. Okay. The other important thing, guys, when you see these type of problems, we have to make sure that we do recognize them, and we do recognize them as what I call impulse calculations. Okay. So, Ty, I think we'll take a short break now, all right? Mm-hmm. And I'll come back and I'll run through a whole lot of worked examples.
All right. No problem. So mindset is, as you heard from Bruce, don't go away. There's a lot more work to come up. So, pens, pads, when you come back. Also, don't forget your phone so you can get on the Facebook page and chat to me. But for now, we'll see you after this break. Okay. And welcome back, Mindsetters. Hope you had a nice little break there. And you're back, you're ready, you're good to go. You've got your pens, pads out, and you've got your phone next to you so you can make sure that you can send in those questions via Facebook. But Mindsetters, do not forget, keep on posting on the page, because I have these awesome prizes to give away, this Casio calculator and this labeler. So please make my job easy and just post on the page. But for now, I'm going to hand you over to Bruce. Bruce, take it away.
Right, Ty, thanks very much, guys. And I hope that last session wasn't too intense for you guys in terms of the theory. It's very important theory, okay? But if we get it right, guys, the problems really can become quite simple. And what I want to do is just to spend a little bit of time going over a few problems and just looking at some typical type of questions that you could be faced with in a test or even your end-of-year exams, just to make sure that we do understand this properly. Okay, so what I've got over here is a very simple little question. It says a hockey player applies an average force of 80 newtons to a 0.25 kilogram hockey puck for a time of 0.1 seconds. Determine the impulse experienced by the hockey puck. Now, you might say, well, what's a hockey puck, guys? Well, this question actually came from an American textbook. And you remember, guys, in America, they all love to play ice hockey. So they don't actually use a ball like we do, where we play field hockey. They play ice hockey with our ice hockey puck. Okay, so what's basically happening is that I'm going to draw a little picture. And there's the ice hockey puck. It looks like a little rectangular object. Here's the hockey stick. Okay. And basically what's happening is that 80 newtons of force is being applied to that hockey puck, and the time the length of time that hockey stick makes contact with the hockey puck is 0.1 seconds. So there now, guys, is the force that's acting on the object. Now, guys, that force is what's going to accelerate that hockey puck, because that hockey puck was dead still. Now, we're going to accelerate it. So this has to be now a net force. Why is it a net force? Because it's the force that's going to cause the hockey puck to accelerate. So therefore now, they want us to work the impulse experienced by the hockey puck. Now remember, guys, that impulse, okay, is equal to F net times delta t, where delta t is the time it takes for that hockey stick to have contact with that hockey puck. So therefore, my F net is going to equal 80, because that's the accelerating force. My delta t is 0.1 of a second, and therefore, we are now going to have an impulse which is going to equal 80 times 0.1, works out to be 8, and now we come to the unit of impulse. Okay, well, we all know that force, we always measure force in newtons, don't we? Okay, that's an old one, everyone knows that. Now, time, we measure in seconds. Okay, which is lowercase s. So therefore, what is now going to be the unit of impulse? Force times time is the Newton second. And there, guys, is how we can simply, given force, the resultant force or net force, and the time that that force acts, we can work out the impulse and we measure it in Newton seconds. Okay. Now, that was a pretty straightforward question. That was just sort of a nice little warm-up into the next one. Because the next one is definitely a little bit more challenging. Whoops, let's not go too far. Where it says here, Jennifer, who is a mass of 50 kilograms, is traveling at 35 meters per second in a sports car when she must suddenly slam on the brakes to avoid hitting a deer crossing the road. She strikes the airbag, okay, which brings her body to a stop in 0.5 seconds. So obviously the airbag's been deployed here. What is the average force, or what average force does the airbag exert on her? Okay, now that question is a little bit more complicated. But if we have a look at it very carefully, let's see now the important parts of it. Well, we've got a mass, okay, and we're traveling at an initial speed of 35 meters per second. She slams on the brakes. So straight away, if she's slamming on the brakes, guys, she is applying a force. And braking, guys, is a force that slows down the object, in this case, the sports car. So therefore, slamming on the brakes must be equivalent to a resultant force acting on that sports car. I hope you guys are happy with that. She strikes the bag, and it brings her body to a stop in 0.5 seconds. So there's the time, and it brings her body to a stop. So guys, can you see now? We've got information about two velocities, an initial velocity. So let's write this down. Initial velocity of 35 meters per second. She has got a final velocity of 0 meters per second. She's got a total body mass of 50 kilograms. Okay. And they are asking, or they're giving us, the time it takes to bring it to a stop is 0.5 seconds. And they're asking us, what is the force? And guys, It has to be a net force because it's a braking force, and the braking force is bringing us to a stop. Okay, so therefore, guys, we've got lots of information. What are we going to have to use? Well, straight away, because we're needing to work out the net force, I'm going to be using my impulse equation. And there it is. F net times delta t, the impulse is equal to the change in momentum. Again, I'll say it and have a look on the board. The impulse, which is F net times delta t, is equal to the change in momentum. And how do I know we need the change in momentum? Because my velocity's changed, guys. We've got an initial velocity of 35 and a final velocity of 0. It came to a stop. So let's now plug in the values. F net is what we're looking for. Okay. Multiplied by the time. Well, that time to bring it to stationary was 0.5 seconds. The mass was 50 kilograms. And remember that, and I'll put it over here in a different color, that delta V is equal to VF minus VI. Okay. So therefore, what's going to be VF? VF is 0 minus VI. VI is 35. Okay. Let's get a bit more space here. All right. Therefore, F net, whoops, sorry, go back to the pen. F net is going to equal 50, okay, multiplied by minus 35 divided by 0.5. Okay, so let's bring up the calculator and let's do this together. Let's clear it up. So we've got a value of 50, okay, multiplied by minus 35, okay, and that gives us now a value of minus 1,750. We divide it by 0.5, and we get an answer of minus 3,500. Okay, so my net force, whoops, pen back, my net force comes out to be minus 3,500, and because it's a force, it's measured in newtons. But guys, remember what I said earlier. We have to interpret the negative sign in the answer. And I gave you a clue right in the beginning when I said applying the brakes. It's a force that's slowing the object down. It's a force that's going to cause a negative acceleration. Okay? In other words, the force is acting opposite to the direction of the motion of the car. It's a retarding force, guys. And that negative sign over here is telling me that the net force is actually acting backwards, opposite to the direction of motion. So I can write it down as 3,500 newtons opposite. Whoops, sorry. Let's get the spelling correct. Opposite to the direction of motion. Okay. And guys, it is important to actually put that direction in. If you wanted just to turn around and say, well, why don't we just say it's backwards? Well, that's fine as well. All right, but it's always nice to get our physics nice and correct and say opposite in the direction of motion as well. Okay. Now that, guys, hopefully has given us an idea of how we can use the impulse formula and the impulse calculations that go with it. Very important, guys, that we are able to highlight the important facts about impulse. Now, I just want to go back back a slide, or on that slide, to go back to my original bit over here. Okay, there it is. In this statement, the quantity F net times delta t is known as the impulse. And this, guys, historically is where I found people have started to struggle. Okay, they think impulse is this new, big, magical term that comes out. Guys, it isn't. It's very simple. Your impulse is actually equal to the change in momentum. Remembering always, guys, that a change in momentum can only occur if a net or resultant force acts on an object over a certain amount of time. And that is where our equation comes up. F net equals, multiplied by delta t is equal to delta p, my change in momentum. And there we now have our equation for the impulse. And I hope, guys, that this has been of some help to you. Okay, very important, because I'm almost guaranteed that you guys are going to get a question in your end of year November examinations, and it's very important to get these right. Time, that's basically all I've got. Hopefully you've had lots of questions, and I'm sorry, because it's been a bit of a rush show, because I've had so much to tell you guys, I haven't really taken many callers.
Well, it's not a problem. Like, the great thing about it is that what I'm seeing is that the mindsetters have been helping each other out and
Awesome,
answering each
awesome,
other.
awesome.
So mindsetters, awesome. You know, I always encourage that. So make sure you guys stay tuned and keep on posting. Use the page. Guys, it's for you. So make sure you keep on using the page. I want to thank Liberty. Thank you for sponsoring the show. And from me, Ty, and Bruce, thank you very much. And we'll catch you next time. Cheers.